right, so we are going to take up from where we ended from. So I'll just start from talking about the covalent bond. Okay, so as you well know, when we talk about covalency, okay, this is a union between two or more things actually, that are connected. So in this case, we're actually talking about bonds. So a covalent bond is a chemical bond that results from, the key thing that I want you to get from here is equal sharing. Okay, so there must be equal sharing of electrons. Okay, so if there isn't equal sharing of electrons, then that's not covalent. So we have a single covalent. So if it's single, it means, for instance, you have hydrogen here and another hydrogen there. It means you have two atoms that are sharing two electrons. So this is a single covalent, which is denoted like this. This is a single covalent. Alright, so usually formed of atoms that are alike, like we have seen, but they can also be amongst atoms that are different. So usually from two atoms of different elements, the hydrogen molecule that we have aligned has a single covalent bond in which two electrons are shared equally, like you can see here. Okay, so we also have methane. Okay, methane is like this. So methane has single covalent bonds. Okay, so we have two electrons here, 2 2 2 2. Okay, so this is the CH bond is such that in each CH bond you have two electrons being shared. Okay, so these two electrons will be shared, and we have how many CH bonds? We have 1, we have 2, we have 3, and we have 4. Okay, so we have 4 CH bonds, and each bond is sharing two electrons between the two atoms. Alright, so this is how the bonds are shared, and always remember that when bond formation is taking place, every atom wants to attain what we call the octet rule. Okay, so this is actually more explained in chemistry more than it is in biology, but we'll just look at it for the sake of understanding this concept. So the octet rule is that this carbon should have a maximum of 8 electrons in its outermost shell. Okay, so as you all know, carbon has 4 electrons in its last shell, so it means it needs 4 more electrons. So these other electrons will be donated by these hydrogen atoms that you can see here. Okay, that means it would have completed its octet rule already. Okay, so we'll also look at another atom or molecule rather, nitrogen. Okay, so nitrogen has 3 covalent bonds. Okay, and if we know that each bond is carrying 2 electrons, so it means there's 6 electrons right here. Okay, so nitrogen has 3 covalent bonds, and each bearing 2 electrons each. Alright, so this is nitrogen with these lone pairs, which are electrons that are not involved in the chemical bonding. So the next thing that we're going to talk about is non-covalent interactions. So just wanted you to appreciate the fact that covalent bonds can not only be single, double, but they can also be triple, as long as the atom is sharing equal electrons with its fellow atom in order to attain the octet rule. Okay, and you must know the reason as to why these atoms actually form bonds in the first place. It's because if you have carbon here and it has 4 bonds, okay, or 4 electrons, in this state it's not stable, so it actually opts to making or rather forming bonds to be more stable. Okay, Okay, so I'm sure you appreciate this more as you go in organic chemistry, because if you have carbon in such a case where it's only attached to three things, you find that this carbon is going to be reactive, okay, because it still has electrons that can participate in a chemical bond, but this one is non-reactive, okay, because all the bonds are filled up. This one is sharing electrons with this one, and so on and so forth. Okay, there is no space like this one has. So the next thing that we are going to talk about is the non-covalent bond. So non-covalent bonds. All right, so under these bonds we have the four main types. The first one we'll talk about is hydrogen bonding. Okay, the second one that we talk about is van der Waals. Thirdly, hydrophobic interactions. And lastly, we're going to talk about ionic bonds. Okay, so these are some of the examples that we have. Okay, so when you look at these bonds, we're actually going to talk about them each at the personal level. So firstly, start by talking about the ionic bond. All right, so the ionic bond. Okay, so when you look at this type of bond, it's formed by the interaction of oppositely charged atoms or groups of atoms. Okay, so the atoms will be oppositely charged. Okay, and according to the laws of magnet, the opposites charges, they attract each other. So if you have an ion that is positively charged, for instance sodium, and another ion which is negatively charged overall, which is chloride, these two atoms are going to get attracted to each other and they'll form a bond, which is sodium chloride. So this bond is what we are referring to as ionic bond, because these two bonds, they are not, so note that there is no sharing of electrons in this case. Okay, no sharing electrons, but what is happening is that there is a bond that is formed, not because they are because they're not sharing electrons, but because the attraction is formed between two opposite charges, that you can see the positive and the negative. Now we need to look at some key things that can qualify a molecule to be ionic. Okay, so what you note that when an atom gains or loses, so we look at sodium for instance. If sodium has, let's take for instance, it has 8 electrons. Okay, when sodium has 8 electrons, you find that when sodium loses 1 electron, it will now have 7 electrons. Hence, in its outermost shell, so if this is the first shell, you have 1, 2, then the other ones will be 3, 4, 5, 6, 7. Well, let me just write it here. Okay, so 7. So sodium is going to be searching for one more electron so that it will be stable. So because it has lost 1 electron, it's going to gain a net positive charge. Okay, so let me just elaborate more on what I mean by it gains a net positive charge. So you know that if this is sodium, in the nucleus of this sodium we have, let me now give the best example. We have the atomic number being 11, the mass number being 23. So the atomic number is 11. So it means the number of protons are 11 and the number of electrons are also 11. So if you have 11 protons, and we know that protons are positively charged, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You also have 11 electrons. Okay. Now, when all these electrons cancel out, what I mean by cancelling out, they'll form something neutral. Because when you have a positive plus a negative, all you have is a 0. It's as good as when you walk one step ahead and go one step behind. There is no movement there because you have gone back to the same position. It's the same thing. So all these will cancel out. Okay, this atom is neutral. So what you notice is that immediately you remove one electron, okay, from sodium. This positive charge that was pairing with this electron, it will now remain without an electron to pair with. Hence, the overall charge of this atom is going to be positive. Okay, because all these are cancelling out and the only charge remaining is positive. Hence, sodium will be positively charged. So the same thing will apply when we talk about when an atom gains. So before I talk about that, we call ions that have gained a positive charge, we call them cations. Okay, these are cations. Okay, the next thing that we'll talk about is the negatively charged ions. Okay, so here we'll now talk about the negatively charged ions. So what you notice that the best example I'll give is for chlorine, where you have, for instance, if there are 7 in the outermost shell, it means this chlorine needs an extra electron for it to become stable. So the same thing is going to apply. So the atomic number is 17. Okay, so it means where we have 8 protons, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, we'll equally have corresponding electrons. So what you notice is that a complete octet rule, it's either we have 18 electrons. 18 electrons means it's a complete octet. Okay, according to this formula, 2n squared. Okay, this can give us the number of electrons that can occupy the shells of that atom. So what you notice is that when this if there's 17, whenever it gains an electron, all these will cancel out. Remember, positive and negative, they're all cancelling out. So the overall charge is going to be negative. Okay, so these negatively charged atoms, we call them anions. Okay, so these are negatively charged atoms. Alright, so this is all about ionic bonds. It's an attraction between oppositely charged ions or atoms. So the next thing that we're going to talk about is the hydrogen bond. Okay, so have what we call hydrogen bonds. So when you look at this hydrogen bond, it's an interaction of a partially positively charged atom and a partially negative atom. So it means for something to qualify to be a hydrogen bond, it has to be dipolar. It must have 2 charges on it. For instance, water. So we have H2O, where the oxygen is the central atom. We have hydrogen here. So we also have lone pairs, okay, which are electrons that are not involved in chemical bonding. So because oxygen is more electronegative, okay, it means it's going to attract the electrons strongly to itself. And because the electrons are being pulled towards the oxygen, okay, it means they will leave a slight positive charge on the hydrogen. And because the oxygen is gaining more electronegative charges, the overall charge it will have will be negative. So it means this entire water molecule is going to be dipolar. Okay, it's dipolar. Di means two. Polarity is where we're talking about positive or negative. So it's got two poles, the negative pole and the positive pole. So if it has two charges, it means it can equally get attracted to a different water molecule due to opposite charges. Okay, all right, so let me just highlight this. So if we have another water molecule here, it means the positive end of this water molecule is going to be attracted to the negative end of a different water molecule. And the same is so to say for the hydrogen. The hydrogen will keep getting to be attracted to the oxygen. Okay, so this is hydrogen, oxygen. So these weak interactions that you can see, this bond, okay, due to oppositely charged atoms, because the atoms are slightly positive and slightly negative. This is what we call a hydrogen bond. Okay, the hydrogen bonds are what qualify this. Okay, so this is a hydrogen bond. So what you notice that there is no sharing of electrons, but a bond is being formed because there is an attraction between opposite charges. Okay, and these opposite charges are coming out because the individual atoms have two either slightly positive or slightly negative. All right, the next bond I'll talk about is van der Waals. So these are van der Waals interactions. Okay, so when you look at these, when any two atoms approach each other closely, so any two atoms, regardless whether they are neutral, so let's take for instance this is a metal, right? A metal and another metal. Okay, what you notice that in this metal we have equal number of charges. We have electrons and protons, and okay, so we have a negative, positive, 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 negative, negative. So we have all types. So what you notice is that when two atoms approach each other, they create a weak non-specific attractive force. So because this atom has negative charges, when it comes to this atom, all the electrons are going to gather at one side because they are attracted to the protons in the next atom. Okay, so there will be this weak interaction. So notice it's weak because the interaction only comes about when two atoms are close. Okay, so when these two so it's non-specific. It means it doesn't really choose what type of atom to bond with. As long as the two atoms are in close contact, there will be an interaction such as this. Okay, so such non-specific interactions result from temporary because they are not for a long time. So it means immediately you separate these, the electrons and the protons will go back to the way they were and they will no longer be attracted. And this is to tell you that when the atoms are far apart, there will be no interaction or no attraction for each other. So the van der Waals interactions are responsible for the attraction between molecules of non-polar liquids and solids. So you know that non-polar liquids or solids, they don't have a charge. So the only way they can get attracted to each other is when they come close in such a way, in what we call the van der Waals forces. Okay, this is what we mean. So the last type of bond that we talk about is we'll talk about the hydrophobic. So this is hydrophobic interaction. Okay, so hydrophobic interactions are actually non-polar. So key thing, non-polar molecules or non-polar portions of molecules tend to aggregate. So when they aggregate, they come together. So if this is an atom, it's non-polar, they will come together. Okay, they'll aggregate. Okay, so they aggregate in water in a phenomenon that we call the hydrophobic effect. Okay, so in aqueous environment, so in an aqueous environment, what you notice is that it's an environment where you have positive charges and negative charges. Okay, now because this atom is non-polar, it means it has no charge at all. They'll come together, okay, because they are they repel. So the best example I can give is a phospholipid bilayer. Okay, so when we talk about a phospholipid bilayer, we have what we call a phosphate group. Okay, a phosphate group. Okay, that's attached to a hydrocarbon. Now what happens is that if this is water, okay, the same thing that happens when you put cooking oil in water, it forms what we call a micelle. So they look like a cylindrical, sorry, not a cylindrical, a circle kind of. So this is our water, this is what happens. Okay, so these circles, this is just, I've now magnified it. Okay, this is a magnification of what is happening here. So all the hydrophobic ends will come together, they'll shun away from water. So they are water hating. That's why they're called hydrophobic, water hating. So though these are the hydrophobic ends. These ones that you can see here. Okay? These are hydrophobic. So they will shun away from water and they'll come together. Okay? These are coming, they'll face each other like this. While the hydrophilic ends, which are the water loving, they're the ones that will face the water, okay, because they'll interact. So the hydrophobic effect happens when things are non-polar, when they aggregate. Okay, so atoms that are hydrophobic are those that don't have charges. For instance, carbon dioxide, we also have other types of gases. Okay, maybe let's take for instance oxygen. It also falls under this hydrophobic effect because it's non-polar. So this is what you notice about the hydrophobic effect. So it's mostly observed in non-polar molecules that dissolve in an aqueous solvent. Okay, so this is how they all gather and actually shun away from water, like you can see, or rather an aqueous. So this is why you find that if something is non-polar, it will never dissolve in water, just like oil. They will not interact because they have nothing in common. This one has no charges, but the water has charges, so there will be no interaction. So this is all about the hydrophobic interaction, and overall these are some of the non-covalent bonds that have actually been discussed. So we firstly talked about covalent bonds as being equal sharing of electrons. We also talked about the types of non-covalent bonds, which is just actually the opposite of these covalent bonds that we were talking about. Then we also have talked about them in details: the hydrogen bonds, the van der Waals, the um, and the hydrophobic interactions. So these are the types of bonds that we have that are non-covalent.